everyone. Here in this session we'll be studying about grain size distribution by sedimentation analysis. Already we have studied grain size analysis by sieving method, which is called sieve analysis. In this case we'll be studying sedimentation analysis. What it is for, how it is different, we shall see the details. Sedimentation analysis. Here we actually mix distilled water and the soil, of which we have to do grain size distribution. Put that soil into the water, thoroughly mix it, and make some observations. This is called soil suspension, and we use what is known as a hydrometer to measure the density or actually specific gravity of the mix. Now, how all that will help you in sedimentation analysis or grain size distribution, that we are going to study in detail. So sedimentation analysis is used for grain size distribution of soil having particles smaller than 75 microns. It is also called wet analysis because in sieve analysis it is a dry. Right here, wet analysis in the sense it is inside the water, we put the soil and then we try to gather the information so that we can find out grain size distribution of the particles which are lesser than 75 microns. Rather, the particles in the range of 0.2 microns to 2 microns will be analyzed. I'm going to give you all those details. We'll go step by step. Okay, the word soil suspension is used for mixture of soil and good amount of water. You can see here almost 1000 capacity this jar, and then we mix in actual test also. We mix just 50 grams of soil into that. Okay, so soil suspension means it is a mixture of soil and distilled water. That has to be kept in mind because often we'll be referring to soil suspension. Okay, now particles of soil settle down with some velocity in the soil suspension because when soil is added, obviously the particles will be trying to settle down. This process of settlement of the particles is known as sedimentation. Because when it settles, what gathers here, we call it as sediment. So what is sedimentation is the process with which the particles settle down with their own velocity, right? It is called sedimentation. Now this property of sedimentation is used for grain size distribution. Of course, we'll be seeing the details now. This method is used for soil having particles smaller than 75 microns. Okay, we'll go further. You know this formula F equal to ma Newton second law. In short, if there is a object of mass m, right, then if it is applied with a force, if you have some mass m and if you apply a force F, then what happens is if it is capable, obviously this moves in the direction of the force, the motion will be having an acceleration a. That is what it means, right? If the force is applied to a mass, it will be getting accelerated in the direction of the force a, right? So it is an acceleration, not that body was rest or motion, nothing. If there is an object applied with a force F, the effect of this force is to gain an acceleration of A. And relation between this F, M and A is F equal to ma. Very simple. Okay. Now I'll remove this. The velocity of settlement of the particles depends upon size, shape and weight of the particle. This is an important factor in sedimentation analysis. Here I have shown a bigger particle, smaller, and then still very small particle. Like that, size as well as shape. Shape I have considered here all wrong. You know that soil particles will be having quite a different shapes, especially the particles which are lesser in size, like 75 microns, and then nearing to clay size, like 2 microns. They are flaky in nature, very flat, or they have needle-like structure also. So when particle settles, there are so many forces or factors which play a role. So velocity of settlement of particles depends upon size, shape and weight of the particle also. Means what is the specific weight or density of that material. Uh, that plays an important role in deciding velocity of settlement. Okay. Now because of gravitational force, weight, particles start falling down with acceleration due to gravity. Obvious. If you let fall any object, it start falling down with some velocity, right? The velocity will be directly proportional to the time and acceleration, right? As with respect to time, the constant of proportionality will be nothing but acceleration, right? If you, the simple way of putting it, if you let fall any object, after 1 second its velocity will be 9.81 meter per second. After the end of second it will be 9.81 into 2, because 9.81 meter per second is the acceleration or rate of change of velocity. If you go to the third second, end of the third second, then it will be 9.81 into 3 and so on. Like that, the velocity continuously increases, right, because of the acceleration. Here uh, there is a particle, just I have shown, particle has got weight of 50 newtons and it falls with continuously increasing velocity. It doesn't stop till it gets dropped onto the floor, right? It falls. Okay, now if you put those particles inside the water, like soil suspension, we have a particle, then what happens is there will be other forces which will be coming into picture, not only the weight. Okay, now what I have shown here is the red soil. Okay, here I have an explanation. But as the velocity increases, the drag force increases. Means what? When the particle is falling down, there will be a resistance offered by this medium. Even in case of air, when you allow the object to let fall, depending upon the shape of the object, the velocity with which it falls will be getting arranged. If it is smooth arrow-like object, obviously there won't be any resistance, it falls fast to the ground. But if you got a round plate-like thing, it will not be falling straight down, it will be having a resistance. So depending upon the shape, the resistance will be different. That resistance is known as a drag force, right? The drag force, which will be a kind of a frictional force, you can say, a resistance force, depends upon shape of the object. Obvious, if it is smooth and stream like uh, object, obviously the resistance will be less, and then if you have a blunt object, it will be having a lot of drag force. And then one more thing that comes into picture is buoyant force. When an object is inserted into the medium, for example water, right? So there will be a buoyant force which will be trying to push it up the liquid. And also lastly, the viscous resistance. So for falling objects, there will be a drag force which depends upon the shape of the object, the buoyant force, and also viscous resistance. These are the factors which will be affecting resistive force, right? So the effective force pushing the object down the suspension reduces. Now just now we have seen that there was an object which was falling under the action of 50 newtons. Now that 50 newtons is there, but now there will be reverse forces, right? Now reverse forces will be obviously cancelling that 50 newton. Suppose there is a force of drag which is having magnitude of 20 newtons. Now what happens is effective force which is coming pushing the soil downwards or the particle downwards will be the 50 minus 20, like that. Right. Now we know that F equal to ma. As the force reduces, as the resultant force reduces, the acceleration also reduces, and ultimately it may so happen that it may reach a zero value. Here there are a couple of you can just observe that weight is 50 newton, drag force is 20 newton. Because of that it falls, but still there is an effective force of 50 downwards and then 20 upwards. So 30 newton is still pushing. Earlier it was 50 newton total it was pushing. Now it is 50 minus 20, 30 newtons is pushing. Because of that the acceleration will be slightly reduced. Now, but the motion continues. Means I am telling you this, when the acceleration reaches zero value. See, in this case, the weight is 50 newtons and the drag force is developed is also 50 newtons. Now, how this drag force increases value? Because drag force depends upon the velocity also. Now, as the velocity increases, the drag force also increases. Because of that, it may so happen that ultimately the weight will be completely balanced by drag force. Such a thing has happened now, right? Now what happens is there won't be any resultant force, right? But the motion is still continuous, right? So here, but the motion continues with zero acceleration, with a is equal to 0. It is a constant velocity motion. If a is 0, the velocity is constant velocity motion. The velocity will not increase further. The increase is terminated. Hence, such velocity is known as terminal velocity. Means beginning the particle starts moving with more and more velocity. At some point of time, it continues with the same velocity without any increase in the velocity. That's an interesting part. So when it moves with a constant velocity, we say that it is a terminal velocity or velocity change is terminated, right? Terminal velocity. Okay. Now you can just see here, particle falls fast. Smaller particles will be taking a lot of time to move the same distance of whatever distance we have from top to bottom, right? The particles of bigger size will fall fast, then smaller, then still smaller, will be still in suspension. So like that, the weight of the particle, the shape of the particle, right, and the viscous resistance, all of them play an important role in sedimentation. Here we have hydrometer. I'll tell you about that. Here there is a schematic diagram of an instrument which is known as hydrometer. It is nothing but a glass tube with a glass bulb with lead balls fixed at the bottom. And when you put it into a liquid, it floats with its neck vertical like that. And there are graduations here. Now these markings will be telling what is the density of the liquid surrounding the bulb. Okay, now if you observe here, this has gone down in this liquid more and this has gone a bit up here. So when it is showing like this, more neck on the outside, that is to say that this liquid is heavier or denser, high density liquid. And it is getting inserted too much like that, the density is less. So obviously the graduations over here will be less on the top, more on the bottom. So more values will be here and then lesser values will be here. Okay. So that it should have more of specific gravity at this point, that is when it is sub, uh, immersed into that kind of liquid. But when it goes more inside, obviously the density of the liquid or specific gravity of the liquid over here will be less. So the lesser readings are on the top and then heavier readings or more readings are at the bottom of the neck. Here you can see actual condition, that is there is a soil mixed with water and also there is a actual uh, hydrometer that is let into this soil, right? Some neck portion is floating up and then here there is a lot of portion of hydrometer is completely immersed into the water. Now distance from the point over here, that is the bottom of the bulb, to the surface of the liquid is known as HE, that is effective height of fall. Means the particles when they fall through this distance to go over or go through the particular level. Okay, this sedimentation analysis is based on the principle of Stokes law. Now what is Stokes law? Stokes law states that the terminal velocity with which the soil particles settle in suspension depend on shape, size and weight of the particles. I have told you what is suspension. I have told you what is terminal velocity. When the soil particles are settling, they attain some value of velocity which is constant in the suspension. That is called as terminal velocity. So Stokes' law states that terminal velocity v with which the soil settles depends upon shape, size and weight of the particles. Now here actual the law is converted into expression. The terminal velocity of sinking soil particle will be given by v is equal to gamma s minus gamma w d squared minus 18 mu is equal to He divided by T. He is nothing but this height through which the soil particles fall, and then we'll see the procedure. Once you put the water and soil mixture like that, we'll start the stopwatch and we go on taking the reading, right? So that T is over here, it is time of sedimentation, right? As the time increases, more and more particles will be settling of lesser and lesser size. Now if that is He divided by time is velocity of the particles, right? Because if there is a bigger particle, it suddenly goes down. If there is a smaller particle which will be taking minutes and seconds, obviously it will be very slow. Now He by T, the velocity of fall or sedimentation, is given by gamma s minus gamma w into d squared divided by 18 mu. Gamma s is unit weight of solids. This is unit weight of water. Unit weight in the sense specific weight of water. D, the diameter of the uh, particle which is falling down. 18 mu. Mu is the viscosity of the liquid. Okay. So height of settlement, that is time of settlement. Now here V is terminal velocity, D is the diameter of soil particle. Obviously it is an average diameter because you have different sizes. Unit weight of soil particles, I mean gamma s is unit weight of soil particles, D is the diameter, done. Gamma W is the unit weight of water, G the specific gravity of soil solids, and mu the viscosity of water. This velocity V is calculated as a ratio of He, the height of suspension, to the time of reading. Based on the velocity of settlement, the diameter of settled soil particles may be computed because time and then diameter are related, right? For the purpose of evaluating velocity of settlement of soil particles, hydrometry analysis is used. But most important part is this note. I'll read it for you. In this explanation, I have taken some numerical values for better understanding, and these values may not be correct in reality. The correctness of the values is not okay, but the emphasis is on the principle. So please take care of this. So don't say that how can this value be this. Just for the sake of understanding, you take the value and go ahead. Otherwise, it may look absurd at times, but whatever principle is there, that can be understood through this discussion. So let us say we have 1000 ml or 1000 cc of distilled water. Here I have a jar 1000 ml. It possesses a mass of 1000 grams. Obviously the distilled water has got density of 1 gram per cc, that is 1000 gram per 1000 cc. So to say 1 gram per cc, 1 kilogram, 1 liter of distilled water should weigh 1 kg, right? That is the idea. Or you remember that density of water can be told as 1000 kg per meter cube or 1 gram per cc. Then we have let us say we add 50 grams of soil to this, right? This 50 grams of soil is so taken that it is passing through 75 microns, right? Let us say that it is mixed properly, and then once you keep it, you should not touch in between for hours because the readings are being taken for many hours. So you should not touch this or displace here and there, move this one. You should just place it and then just take the readings with the hydrometer. One should not change the place of the jar again and again. So total mass is now 1050 grams because when you add soil, the mass becomes 1000 plus 50, 1050 grams, and the volume, hardly there will be any change in the volume. It will be 1000 cc itself. So hence density of the suspension will be total mass is 1050 grams and then volume is 1000 cc. So we can say that it is 1.05 grams per cc. Okay, let us say after 5 minutes, this is important because we allow the time. We once you place the jar, you start the stopwatch or make a note of the time, and then whenever you take the reading, you have to make note of how much is the time that is elapsed. Now I say that after 5 minutes some of the larger particles have settled. Now with respect to this time, obviously whatever particle that was there with some size might have come down right up to this point. Let us say that particle size is 50 microns. Okay. Now if 50 microns particle which is there here can come right up to this, obviously any other particle which is having size bigger than this, that is 50 microns and above, will be obviously have settled down earlier. So 50 microns is related to 5 minutes. That is what the point is, right? So in 5 minutes all the particles of size 50 microns or larger will not be there in the suspension. All of them would have settled. All of them would have settled. This is a very interesting point here. Now let us say now the density of suspension reduces to 1.04 grams because some of the particles have settled down right at the bottom. So in suspension there will be lesser soil. The density of the suspension will be reduced. Let us say it has reduced to 1.04 grams per cc. Now the volume of suspension is still 1000 cc and we are telling that 1.04 grams per cc. What would be the total mass of this? Total mass of this will be 1040 grams because 1.04 multiplied by 1000, that will be 1040 grams. Okay, or we'll calculate this way also. The difference in density is 0.01 because 1.05 was there earlier. Now it has reduced to 1.04 grams per cc, so that we can say 0.01 grams per cc is the density which is reduced. Now where this has gone? This is nothing but the particles which have settled down. We can calculate total mass of the soil settled down equal to, this is 0.01 gram per cc, but we have got 1000 cc, so 0.01 multiplied by 1000, that is to say 10 grams. So total mass of the soil which is settled down becomes 10 grams. Out of 50 grams taken, 10 grams already it has settled. Now how much is the soil which will be there in the suspension? Obviously it will be 40 grams. The soil which is still in suspension will be 50 minus 10, that is to say 40 grams. Now this part of the soil which is in suspension is obviously lesser than or finer than 50 microns because particles of 50 microns have gone down, but the particles which are lesser than 50 microns are still in suspension. So I can make a statement. So percentage finer than 50 microns will be equal to the 40 grams of 50 grams multiplied by 100, that is to say 80%. So what I have is percentage finer with respect to size, and you know that in grain size distribution we have two axes, right? If I have to draw that graph, one is x-axis where the size d is plotted. Here there will be percentage finer. This is equally distributed because we have hardly 10, 20, 30 like that, it is 100%. But this is in log, means if you say that this is 1, this will be 10, this will be 100, this will be 1000 and so on. If you say this is 0.1, then this will be 1, this will be 10, this will be 100. If you say this is 0.001, this will be 0.01, this will be 0.1, this will be 1. Like that the graph is there. Percentage finer is plotted here, but here all the size particles like we are taking, have started with saying 50 microns and so on, right? And so down size, all those sizes can be plotted here. Now let us go further. Similarly, after another 10 minutes, means we have up to this point, I told you that we have spent around 5 minutes. Now we'll wait 10 more minutes. If the density is found to be, means using the hydrometer, if I am able to find out the density, means the purpose of hydrometer is that found to be 1.03 grams per cc. The mass of soil settled will be 1.05 minus 1.03 multiplied by 1000. So to say 20 grams in addition is settled down, right? In 10 minutes, let us say particles, in 10 minutes, let us say particles of size 40 microns or larger will have settled down. The mass of soil in suspension will be 50 minus 20, so to say 30 grams. So percentage finer than 40 microns will be 30 divided by 50 into 100, 60%. That is the idea. Okay, sedimentation analysis. Here, in this test, dispersing agent of 33 grams sodium hexametaphosphate plus 7 grams of sodium carbonate is added to 1 liter of distilled water to make soil suspension, so that each particle settles independently without clinging to the other particles. Because if they cling together, the total weight will be more, because of that they settle together slightly faster. If two or three particles come together, the total mass of that flocule will be larger, because of that they settle down. Will not be able to get the correct idea, because of that we add dispersing agent, right? So that every small and big particle will be separate and independent, so that they will not touch each other or attract towards each other. Now mechanical stirrer is employed to mix the soil suspension thoroughly. Means once you mix the soil, you cannot just use hand or mix it manually. You should use a mechanical stirrer with a motor. It has to be mixed thoroughly, and then it will be placed into the jar. The mixture is transferred to 1000 ml measuring glass jar, vigorously mixed, and let the jar made to stand on the table. Here we assume all different size particles are equally distributed everywhere in the suspension. Means when you mix it, you have to hold a hand on the top and then mix it thoroughly, up and down, twist it, and then put it. The moment you put it, you start the stopwatch. So we make an assumption that everywhere the particles are equally distributed. Whether you take density at this point or density at that point, it is one and the same. That's what it means. Okay, limitations of sedimentation analysis. Because we use Stokes' law, there is some kind of limitation. First one, all the soil particles are not spherical as assumed. Finer colloidal particles are flaky and needle-like in shape. Specific gravity of different particles vary in its value, but for calculation, average value is used. Specific gravity of different particles will be different, right? Average value is considered for the sake of calculation. Interference of the boundaries of walls of jar will affect the velocity of fall of the particles. Means if the particle is trying to touch the side wall, there will be greater disturbance. If it is centrally going down, then it will be moving faster. So interference with the boundary will affect. Next is interference of the surrounding particles will affect the velocity of fall of the particles. Means if it is not a single particle will be given and then led to fall, you got number of particles, that's why. Now the Stokes law is not applicable for the particles smaller than 0.2 microns and for those whose size is greater than 2 microns. Look at this. If the particle size is more than 2 microns, you will not be able to use this sedimentation analysis. If the particle small is zero point 0.2, less than 0.2, then what happens is there will be 0.1 microns, etc., and hence the Stokes law is not applicable because of Brownian motion of smaller particles. When the particle becomes smaller, surface forces will be playing a predominant role rather than weight. Hence, the particles will be settling very slowly. Okay, here there are some corrections to be put for hydrometer reading. The recorded hydrometer reading may require the following corrections depending upon the situation. So what are the corrections? CM, the correction for meniscus, CT, correction for temperature, CD, correction for dispersing agent. Now what are these? The solution containing soil will be opaque. Obviously you will not be able to see the meniscus bottom properly. Hence it is difficult to obtain reading corresponding to the lower meniscus. RH is taken to upper meniscus and correction is applied. The correction is always positive. Okay, next. However, it is calibrated at 20 degrees centigrade. Hydrometer is calibrated at 20 degrees centigrade. It is if the laboratory temperature is higher, the liquid will be less viscous and hydrometer sinks more. RH will be less than the actual needing positive correction. RH will be less than actual needing positive correction. Similarly, low laboratory temperature requires negative correction. C4, CD, the correction for dispersing agent. A dispersing agent added to water to disperse the soil particles and allow them to settle individually. Dispersing agent increases the density of the water and hydrometer floats higher. Therefore, the correction is always negative.